Learners, and welcome back to another PChem recitation video. I'm going to go ahead and just jump right into the content that we got this week and get this going. So for the first thing we're going to talk about is something that we've talked about in class, which is excitation. So I want you all to think of this in terms of spectroscopy, because a lot of you are having trouble conceptualizing what the different components actually mean. So remember that c, or the speed of light, which is 3 times 10 to the 8th meters per second squared, is equal to nu times lambda, which is your frequency times your wavelength. So just basic things to think about for that. Keep that in mind as we go forward with our calculations. So let's think about the two different types of spectroscopy that we're going to use in this example. So for NMR versus UV vis. So NMR has a longer wavelength, which means that it has a smaller frequency, and therefore the energy is lower. So when we have a lower energy, that means that we're going to indicate that we have a higher ratio of closer to 1 for our ratio of upper to lower. So basically this means that NMR is not a sensitive technique, because the energy transition between the two is not a whole lot. So you're going to have stuff getting to the excitation state very quickly, and that means that you don't have to put in a whole lot of energy and you're going to get a lot of excitation. So overall, UV vis is going to be a much more specific technique to use and will be a lot more sensitive. Okay, so let's talk about some of the energy calculations that we've talked about in class. So our energy that comes from the electrostatic, we can use the 1 over 4 pi times epsilon naught times Q1, Q2 over R1, R2. So important things that I want to point out with this epsilon naught value is going to be your permittivity constant. So this is going to be dependent on what type of solution you're in, or if you're in a vacuum or something like that. So overall, this part of the equation you're going to use if you're in a vacuum. The Q1 is going to come from your first charge that you're going to look at, and your Q2 is going to come from your second charge. This includes partial charges. So if you're looking at something that has a partial negative or partial positive, it's still going to work in that capacity. And then this R value right here is going to be the distance between your two atoms. So it is not going to be your van der Waals optimal distance. It is just straight up whatever the distance is between the two. This does simplify, as we talked about in class, to 1,391 kilojoules per mole for basically that first component that you see here. But you can use either one. It'll work out. This sometimes just provides a simpler way of looking at it. Okay, the second equation we're going to look at is the van der Waals. So again, we're going to be using epsilon naught, and for this case, we're going to have this big R, which is the optimum distance between two molecules. So this is going to be your optimal van der Waal distance between them. Whenever you're given two van der Waals radii, you're just going to sum the two of them. So say you have an oxygen and a hydrogen, as was in the problem set. You're just going to take the sum of the two to get your van der Waals radius between the two, or your big R. And then the little r, again, is going to be whatever the distance is that you're actually experiencing. And remember that we use the raised to the 12th and raised to the 6th to designate repulsion and attraction, and they just help to balance each other out mathematically. Cool. Next thing we're going to talk about is selection rules. So when we're talking about selection rules, the thing that we're going to look at is what kind of spectra we're going to get from different types of excitation. So for allowed transitions, we're going to have high probability, which means that we're going to get high intensity. Those two are related to one another. And then this is going to be a very fast transition. So it's going to happen in nanoseconds, and usually it'll reset itself, and you can do this multiple times very, very quickly. A disallowed transition has a low probability and a low intensity. So again, these two are linked to one another, so you're not going to see as big of a peak because it's just not going to happen nearly as often. And it's going to be a slow reset time. So the half-life is going to be pretty long, and this usually happens in phosphorescence because it is not an allowed transition, and you're going to get something that releases energy over a long period of time. Okay, and then this is where this actually comes into play. So when you look at a Jablonski diagram, you're actually going to see these different transitions. So the first thing that you're going to do is you're going to have energy that comes into the system. So some form of light is going to enter the system, and it's going to excite your photon, or excite with a photon, your electron up to a different energy state, which is going to be up here. The important thing to remember is that each of these is made out of waves. So you're going to have a wave here that it has to go from the peak of this wave to the peak of this wave, and that's going to be an allowed transition. Once it gets to the peak up here, it's going to relax, as designated by this blue line, down to the lowest energy in that valley, and then again there's going to be a peak here, and it will transition to the peak in the lower, which again is going to be allowed, and this is going to be your fluorescence. So then you're going to get some sort of light off. Once it does that, again, it will relax back down to the lowest energy state. So when you're within these parts of the Jablonski diagram, so you're going from the higher to lower transition, this is going to be your IR or your heat. So you're going to get this released in the IR spectrum, or you're going to see this in the form of heat. When you have this one up here, this is actually going to be your light that's emitted, so it's going to be fluorescence. We're going to talk about disallowed in an example coming up, so keep that in mind as we move forward. Okay, so this is going to be an example problem, so hopefully this helps you guys figure out a little bit about how we can use this stuff. So in the below question, it says, draw all the transitions for the absorption and fluorescence of a photon. Label all transitions. So what we're going to do is we're going to start with this right down here. So it's going to be our lowest energy, and we're going to move all the way up into the next transition. So this is going to be energy coming into the system. So we know that it's going to be an allowed transition just based on how the question asks it. So you're going to get this shoot up, you're going to look for the next maximum peak, and that's going to be your absorbance value. Once we get to that value, within that well, it's going to transition to the lowest energy point. So it's going to move to this low one down here, and that's going to release some heat or infrared light. And then once it reaches the lowest point, it's going to drop down back to the lower energy well and release fluorescence light. And again, relax back down to the lowest energy point. So that's going to be either heat or IR spectra that's released. Overall, this is a pretty simple setup and should be pretty self-explanatory. Next, we're going to talk about some disallowed transitions. So the thing that you know it is saying disallowed from is this phosphorescence. So phosphorescence means that it's a disallowed transition, and as we said earlier, it takes a lot longer for it to transition back to the lowest energy minimum, and you're going to see light given off or some sort of spectrum given off for quite some period of time. So it's going to start off exactly the same. So we're going to go from our lowest peak to the next peak that we see in the higher energy level. And then what's going to happen is we're actually going to move into a disallowed state. So as you can see over here, this is going to be our pi star transition. And so it's going to move to the lower energy of that other well. Again, it's going to release heat or infrared. But when we actually drop back down, this is where you're going to see the phosphorescence, because this is a disallowed transition from pi star to pi. And again, we're going to relax back to our base energy state, which is going to release some heat or IR. And that's a pretty easy way of looking at these diagrams. There's not a whole lot to them, but you should know if it moves to a different well, you're going to get something that potentially is disallowed, and you're going to get phosphorescence from that. Okay, next one we're going to look at is absorbance. So we talked about this pretty recently in class, but I want to go over it and provide some examples for it. So a protein has a molar extinction coefficient of 10,000 per molar centimeters, A solution of this protein is placed in a cuvette with 1 centimeter path length. The intensity of light is 220 nanometers coming out of a solution that is 10% of that coming in. So first thing we need to do is calculate the absorbance of the solution. So based on what we were given in class, there's a pretty easy equation that helps us to solve this. And this is the absorbance equals the negative log of I out over I in. So in this case, we know that it is 0.1%, or 10%, so 0.1 for our ratio of the two of them. So we just go ahead and plug that in, and we get that A is equal to 1 absorbance unit. Very simple. Okay, moving on to the second part, we're going to calculate the concentration of the protein in the solution. So for this, we're going to be using the equation that you guys are probably pretty used to based on your chemistry classes, but we're going to use A is equal to epsilon times C times L, and we can rearrange that to be C, which is, again, our concentration, equals A divided by epsilon L, and we have been given in the problem that our epsilon value is 10,000 molar centimeter, or per molar centimeters, and then our path length is 1 centimeter. So our centimeters cancel out, and we just get molar. So it's going to be 10 to the negative fourth molar, or 0.1 millimolar. Again, these are pretty simple to figure out equations. You just got to put your brain in a place where you can quickly think about this stuff and move quickly through the problems.